All right, so last time on Friday we left it off with multidimensional arrays. Just to review that really quickly, remember that a multidimensional array is nothing more than a 1D array, a collection of 1D arrays, right? That if you a 1D array can be modeled using a pointer, an int star. And so if you want 2D arrays, then it would be int star star, right? And that would be an array of pointers that points to arrays of integers. The example that we ran through was something that looked like this. And this is the visualization. Where we create a matrix, or call it a table if you want to. And it's going to be an int star star, right? And that's because it's going to point to an array of pointers, each one of which points to a row in your actual table. So, visualizing this, when on line 3, when we initialize the array of pointers here, remember that we're asking for n of them, and how many bytes does each pointer take? Well, if you remember the Valgrind demo that we did on Friday, a pointer actually takes 8 bytes, whereas an integer only takes 4 bytes. So we need to tell it int star, the size of int star, that 8 bytes. We want 10 of those. And then we go into a for loop here. For the first row, we need to initialize that. For the second row, for the third row, for the last row, et cetera, et cetera. Once we're done with that, we can't just free up the matrix. We can't just free up table, because that would mean that we free up this column right here, but all 100 of these elements over here are now lost. It's all going to be a memory leak. So we have to go in reverse. We have to delete each row, and then finally, once we've deleted each row, then we can delete that one column. And that's the code that we wrote last time, right? Where we have num rows for each row here. We have to build our table each row. We set it and we do something with it. We print it out. We do whatever we're going to do, and then we left it off with just freeing the table. Freeing the table would end up just freeing out this one column right here. To do it properly, we have to first delete each row. So first delete each row, ... right? For int I equals 0, I is less than num rows, I plus plus. Right? So for each row, you can delete that row. And that's going to be a free. And how do I free the ith row? Table sub I. Right? Once you've done that for each one, now in the visualization here, I went reverse. Right? That's just because I reversed the animation. Up here, where you can go forward, you can do it randomly, you can do it whatever order you want, as long as you do it for each row. For each row, you free that. Then, once you've freed every single row, now you can free the full table. Right? If I ran Valgrind on this, remember what flag do I need to run to keep for Valgrind? G. Right? And when I run Valgrind on a.out, I see that there are going to be, oops, what did I do? And you said exit. Well, there are no. Okay, I know what's wrong here, but it's certainly not a memory leak, right? The heap summary says at exit there were 0 bytes. All heaps were freed. There are no leaks possible. What it's complaining about here: 240 errors from 5 different contexts. What are the default values of a table or of an array in C? Undefined. 0, likely. I mean, that's what happens when I print out the table, right? Here's the table. 10 by this one is 5 by 10 with 42 in the upper left, 101 in the lower right. All of the rest of them just happen to be 0. That's me lucking out, and this is Valgrind pointing out my error. You relied on luck to get zeros, right? If you actually expect for them all to be zeros, you need to go through the entire table and zero them out. The 40 errors here are me trying to access values in the table that were never set and that don't have a default value as defined by C. Okay. If you want to, we can go ahead and do that. Right. Once you've set up the row, for int j equals 0, j is less than num columns, j plus plus. Right. And I will go ahead and set table sub I. I like calling them tables anyway because the setting of things is much clearer, right? You're setting the table. I'll set them all to 0. Right? Now they are all explicitly initialized. Right? If I compile this again and run it again, I get the same result, of course. But if I run it through Valgrind, I should have far fewer errors. Yep, 0 errors. Why? Because I wasn't just printing random garbage that just happened lucking out here to be 0. I went through and I explicitly set all those values to 0 so that they did have an initialized value. Right? Always initialize your values, regardless of if you're going to use them or not. Right? Well, if you're not going to use them, then you probably don't want to create them. Right? Anyway, here is that code, and I'll make sure that you have it in the notes there. Okay. What we're going to do today is we're going to look at using arrays with functions. You can pass an array to a function and have it process the data in your array and have it process data stored in the array. You can also design functions to return an array. Right? We already have one such function, malloc. Right? Malloc returns a generic void pointer to a bunch of memory that you've allocated for use in an array. We're going to go ahead and do that, but not just malloc. We're allocating memory. We're going to actually do something with it. Okay. So, some notes here, observations before we begin. If you pass an array to a function, you are passing a pointer. Why? Because arrays are pointers. They point to the first element in the array. We'll look at a visualization of this later on for how memory actually works, but that's it, right? If you're going to pass an array to a function, you pass a pointer to the first thing. If I had a billion elements, a billion numbers in my array, and I passed it by value, remember passing by value passes copies to the function. Could I take a billion elements times 4, so that's about 4 gigabytes, can I pass that off to a function? I would be copying it on the program stack. Right? Remember that stack? It's only so big. When you get 8 megabytes, that's it. It's over. You've overflown. After that, you've overflown it. You can't possibly pass even, say, 10 million integers to a function by value. You can't pass copies. So what you have to do is you have to pass by reference, by passing a pointer to the array. What else do you need to pass? You also need to tell the function how big the array is. Why? Because if I just have a pointer to a memory location, there is 0 way that I can tell how big that thing is. I need to be told that there are 5 elements in that array. How am I going to write a function otherwise? Right? So, for example, let's come over here, and let's get rid of this old code. And let's just go ahead and create an array here to play around with. I'll use one array that we've played around with before, primes. Right? Let's go ahead and go with the first 8 primes, 2, 3, 7, or 5, 7. What else? Oops. 5, 7. What else is there? What's the next prime? 11, 13, 17. Is that 8 of them? Nope, 19. There we go. Right. Now, if I'm doing good bookkeeping, I need to keep track of how many things are in that array. In a variable, usually n, or size of array, or size of primes, or whatever. Right? There are 8 in there, right? All right. Did I miss any primes? I don't think I did. All right. So there's an array that I'm going to go ahead and play around with. Now let's go ahead and create a convenience function here first. All right? Let's go ahead and create a function to print an array. Prints the given array of the given size out to the standard output in a nicely formatted manner. Nicely formatted, whatever that means. Right? Readable. So what should I call this function first of all? What's it doing? No? What did I just write that it does? Prints an array. So print array. Right? Now, how do I take an array as input? Would it look something like this? That's one number, right? And it's passed by value. How do I pass in an array? What is an array again? A pointer, int star. What else do I need to tell? Well, let's leave it like this for a second. Right? Now, if you were to print this out to the standard output, what I mean by nice, we'll go ahead and print this nice square bracket at front. And then after that, we'll go ahead and go into a for loop for int I equals 0. I is less than n, the size of the array, I plus plus. Right? We'll go ahead and print f, and then we'll print it in a nice manner here, %d with a comma space maybe, right? And then at the very end, we'll go ahead and print the ending square bracket at the very end. There we go. Let's go ahead and test this, first of all, let's even test to see if it compiles, GCC demo. Oops, I needed to actually print something, array sub I, but that's not what I want to look at here. I want to look at this error right here. It's complaining about n used on line 14. Okay, size of array, is that correct? No, what does size of do again? It gets the number of bytes of whatever you give it. If I go size of int, it'll tell me that that takes 4 bytes. If I go size of int star, it'll tell me that a pointer takes 8 bytes. Size of double, also 8 bytes. What this will do is say, oh, size of array, well, array is an int star, that's 8 bytes right there. Are there always going to be 8 things in my array? Sometimes there will be 3, sometimes there will be 50, sometimes there will be, 2, right? That's not what I want. I want n. And the only way of getting n is to tell it n, right? So prints the given array of the given size, n, out to the standard output in a nicely formatted manner. Right? What's my return type going to be here? Am I going to give you back? Yeah, you gave me an array. I print it out. Do I give you anything back? Nope. So void. There we go. All right. Well, let's now try to compile it. Yeah, go ahead. Oh, thank you. Yep. Is that the only thing I needed? There we go. Yep. All right. All right. Didn't do anything because I didn't actually call the function, but at least it compiled now. So print array, primes, and n. Hey, wait a second. Do I put anything in front of primes? So let's think about that for a second. This expects a pointer. How do I take a regular old variable and change it into a pointer? An ampersand. If I had int x, I would go ampersand x to change it into a pointer variable. But this is already a pointer. Right? Why? Because it's an array. I do not put anything in front of it. It's already a memory address. This is how memory works. We'll look at a deeper example later on here. All right, so if you pass an array, you do not use the ampersand. You just pass the name of the array, and it's all good. Right? So that could be nicer. I could go to the next line after that ending square bracket, and also that Oxford comma there. I don't know, should we have that or not? No? Okay. Then how do I get rid of it? I stop one short, and then handle the last one separately. Ooh, where's the last one? Is it at array of n? N minus 1. Good. Why? Because we start at 0. 1, 2, 3, 4. There are 5 elements in there, but the last index is going to be 5 minus 1, giving you 4. There we go. That's much better. Much nicer. Oops. Sorry, did I not save it? Must not have saved. GCC. Come on. Oh, no, Oxford comma. I was still doing the Oxford comma. All right, there we go. And then I can actually compile it, or just get rid of this and put it into one line. That's a little bit better. Why use many words when few words do good? Right? Why have 2 lines of code when you can get it down to 1 line of code? But then why have 1,000 lines of code when you can get it down to 1 line of code, right? Yeah, don't do that. That's too much. Readable code is always better than clever code like that. Right? All right, so before I move on here, let me show you another thing. So you print it out, fine, but let's also go ahead and screw it up. Array sub I, I'll set that equal to negative 42. Expected or unexpected? Well, that doesn't seem to do anything, right? It printed out normally. Let's print it out twice and see what happens here. Before I run it, predict what's going to happen. Remember, this is being passed by reference. A pointer to the variable is being passed, meaning that the function can change things, right? Remember back to when we started all this with the swap demo. When I was passing by value, I was passing copies, right? 10 and 20. So that the original 10 and 20, they weren't actually swapped. We solved that by introducing pass by reference, using pointers. I am passing not the copies, but actual references to the variables. So you can jump to those memory locations, and you can screw it up as much as you want, like we've done on line 16 here. Right? So predict what's going to happen here. Do changes to the array, are those affected in the main? Yes. We've screwed up the entire array here, right? Not only have we printed it out, but I've also set it all to -42. Should we be allowed to do that in a function that we said is just printing stuff? Should we? Probably not. So what I'm going to do is I'm going to give you another keyword here. You've seen this keyword before. Const. What that does is it makes a promise. I am not going to change your array, right? It becomes a read-only array, a constant array, right? Now, down here in main, you own the array. You can do with it whatever you want. But when I pass it off to the print array, print array is making a promise here that I'm not going to change the contents of your array, right? And the compiler is able to see that. The compiler says, wait a second, you said that you weren't going to change it. That made it a read-only location, a read-only array. But on line 16, you broke your promise. And you overwrote, you wrote to that memory location instead. So it resulted in an error, and it's not going to compile anymore now. Once I take that out, prevented by the const keyword. Right? Once I take that out, then I can go ahead and compile it. And now I have a guarantee. I have a promise. It's not a guarantee. There are ways to circumvent this in underhanded ways, circuitous ways, but I'm not going to go over them because it's a design thing. You made the promise. Why would you break your promise, right? It's your code. Why are you breaking your promise to yourself, right? It doesn't make any sense. So use the const keyword anytime that you want to say, I am not making changes to this array, and you have a 90% assurance that I am not lying to you, right? There are always ways around it, okay? All right, there's our first example. So let's come back over here and make some more observations here. You can use the const keyword to make the array read-only. Right? The function will not be able to make changes to the array. Anytime you want to have that assurance, you put the const keyword in front of it. Okay. Let's see. Let's do something else. Let's actually process the contents of an array and do something simple, like say sum them up. I think we've shown this before, but let's go ahead and do it again. This function sums the elements in the given array of the given size n. There we go. And returns the value, the result. There we go. End. Okay. So sum. I'll just call it sum. Okay. We need to take an array and anything else that might be useful for us. So how do I pass an array of integers, say? Int star array. Except that, are we going to be making changes to this? Probably not. So what could we use that we just learned about? Const. What else do we need if we're going to pass an array to a function? The size of it, n. Right? And what am I going to be returning here if I add up a bunch of elements in an array? Integer, because integer plus integer plus integer is going to result in an integer. Okay. Now let's go back to what we're doing right now. Module 5 and Module 6. Error handling. What is the first thing I should be doing or at least thinking about in every single function? Error handling. What are the types of errors that could result in the input here? So what could go wrong with array? Null pointer. All right, let's check for that. If array is null, that's an error. All right. What's another error condition? Not of the array, but say of n over here. It could be a double, but then that would mean that you'd have to design it like this. If it's a double, like 5.2, then when you pass it to this function, integer truncation takes over, and it'll end up being 5 anyway. You can only ever accept a whole number here. Right? But what about that whole number could be wrong? Or fishy, at least. Or code smelly. Is there such thing as there's certainly not such a thing as an array of size 5.2 elements, right? Is there an array of size -5 elements? Nope. So what could go wrong with n? N could be negative or even 0, right? 0 elements, oh, okay, whatever. Right. All right, do I return an error code? Some error code, right? That's not how I've designed this function, is it? Right? I've designed this function without error handling. So what's another thing that we could return that would make just as much sense? What's the sum of here? Now it's philosophical. What's the sound of a one hand clapping, right? Or in this case, what's the sum of nothing? Nothing. All right, I like that. What else? Give me a synonym for nothing. 0. All right. 0. I like that. Another good answer out there. Could I return null? Am I returning a pointer here? Nope. I mean, under the hood, it'll probably work. There are some systems on which it wouldn't, but it's the wrong idea of nothing, right? We need a different idea of nothing, 0. Wait a second, I thought you said that error handling 0 meant no error. Well, yeah, I mean, you gave me nothing. I'm going to sum up nothing for you. Here's nothing back, right? This makes perfect sense. Right? The sum of nothing is nothing, and the sum of nothing, the numerical value of nothing is 0. Right? But I am still doing error handling here successfully, even though I'm not using error codes. Okay? Otherwise, let's go ahead and sum stuff up. Int total. For int I equals 0, I is less than n, I plus plus, the idiomatic for loop to iterate over elements in an array, total plus equals array sub I. And as I write the last line, tell me what's wrong with this code already. You do initialize total. Why? Garbage plus 1 is garbage, right? So always initialize your variables. There we go. Anybody know what the sum of the first 8 primes is? Int sum total is equal to sum of primes and 8n. Printf, that's a total of %d and line. Anyone do it in their head? I think it was 77. Yay. How could I verify that? Pull out your calculator, do your ad hoc testing, right? How do you design your color tests this week? Pick a color. Husker, Scarlet, RGB value. Right? You just search around for your favorite colors or something. In fact, it'll give you all of your test cases right there. 227, 25, 55. Oh, well, there's CMYK right there. Now that's on the scale of 1 to 100, so you need to normalize it and divide by 100. But there you go. You could also do black, right? But that's, or there, scarlet and cream, right? Pick your favorite color and go with it. Right? Pick a random color and go with that. Right? You just need to do 6 of them. Okay. Those are 2 nice functions. We'll eventually put them in the notes here. But now let's design a function that creates an array. Right? So what I want to do with this is, let me describe the function that I want. This function takes an array of integers of size n and returns a new array containing only even values of the input array. In your documentation, sometimes it's nice to actually give an example. For example, if it was 5, 8, 3, 4, 2, 0, 6, 9, would return The even values in that are what? 8, 4, 2, 0 is even. Right? 6, there. So is it clear what we want? Here's an array of integers. I want you to go through and find all of the evens, and I want you to give me a new array only with those values. In other words, you're filtering out all the odds. You're getting rid of all the odds. But you're giving me a new array. So you need to create a brand new array. You're not just going to go through the old array and then take stuff out, because if the old array had 8 elements in it, right, then you can't just take stuff out. There would be gaps in it. Right? Or you shift stuff down and then there would be unused space over here. I want you to create me a new array that is exactly the size that I need to hold exactly what I want. All right? Let's call this get evens. Okay? Get evens array or whatever. Right? So if I'm going to return a brand new array, what's my return type now? I'm not returning nothing, so it can't be void. I'm not returning one value. I'm returning an entire array of values. So what is an array of integers? Int star. Right? White space doesn't matter. You could write it like this. You could write it like that. You could write it like that. I'm going to write it like this and just be consistent about it. All right? We're going to take an array as input, int star array, and its size int n. Can anybody suggest an immediate improvement here? Yeah, const. Why? Are we going to be making changes to that array? Nope. I'm going to be creating a new array and putting stuff in it, and then giving you back this new array. Okay? All right. So let's whiteboard this. First of all, 1, error handling. That's the first thing that you should think about every function. Even if you're not going to end up doing error handling, you still need to have that thought process in your head. What could go wrong, right? I need to look before I leap. And if it ends up, well, we're not returning an error code here, maybe look at alternatives. For example, what could go wrong here? Exactly the same things up here that could go wrong. If the array that you gave me is null, or if the size of the array doesn't make any sense, then I need to return something. Right? Now, if I were to return -1, right, an error code, is that a value that makes sense as a pointer? No. What if I return 42? I'm returning a memory address 42. That might be a valid memory address that doesn't belong to me. So how can I give you something that doesn't belong to me? Right? Let's rethink this. I'm returning a pointer. What pointer value could I return to communicate that something went wrong? Let's look at something that we're already familiar with, malloc. When I call malloc and ask for 50 terabytes, that's way too much, right? Malloc comes back and says, I can't allocate that much memory. It comes back with what value? No? Where's malloc? Right? I don't know where it is in the notes. Yep, there we go. Thank you. More details. If malloc fails for any reason, it returns null. The only thing that it can. Right? So what should we return here? The only thing that we can. The only thing that makes sense. You gave me nothing, I give you nothing in return. Right? There you go. 2. Help me out. We're outlining now, right? So if we were truly whiteboarding this, I would be writing up on the whiteboard. Step 1, step 2, step 3. What do we need to do now? Well, let's operate on this example over here. So off to on the side of the whiteboard, let's go ahead and simulate what we need to do. All right, I'm going to go ahead and iterate over the elements in this array. 5. Okay, no, that's not even. All right, I don't need that. 8. Okay, 8. I need to put 8 in the new array. 3. Nope, I ignore that. 4. I put that in the new array. 2. I put that in the new array. 0, 6, 9. 0, 6. I put those in the array. 9. No, I skipped that. So maybe iterate over the array. if the element is even, add it to the new array. Right? Pretty simple, right, in English. Let's go ahead and see how complex it is when we actually code this. Right? For int I equals 0, I is less than n, I plus plus, right? The idiomatic for loop to iterate over any array. Right? How do I tell if something is even or not? If I mod it by 2, the remainder should be 0. So it's even. Add it to the new array. Dot, dot, dot. Uh-oh. The new array is equal to, add arrays of I to new array. Do you see a new array? Nope. Okay, so that's okay. On a whiteboard, we can always erase stuff and put a different number there. We need to do something else first, right? We need to create the new array. Dot, dot, dot. How do I do that? I go back to my notes, and I look to see how do I create dynamic arrays here. Right? Oh, no. It's somewhere in here. Here? Nope. Oh, darn it. I never copy-pasted that. Oh, well. It's somewhere. Int star new array, right, is equal to a call to malloc. Remind me, how do I use malloc here? Do I say I want enough space to hold the even integers? Right? It's okay to write stuff like this, especially if you're on the whiteboard, right? You're writing out in plain English. Then you go back and you translate that, right? This is a step-by-step process. Right? You're drafting. When you write an essay in English, right, you don't just write it once and then turn it in. Hopefully you don't. Right? You don't just write it once and then turn it in. What do? You go back and you edit it. All right, well, we don't need that sentence. That sentence doesn't make any sense. Or, oh, I have a disconnected idea in the first paragraph from the second paragraph. I need a paragraph in between there in order to connect them, right? You go back and you draft. We're drafting here, okay? Enough space to hold the even integers. Do I know how big it should be? On this one particular example, I do. 5. But what if it was a different example? What if there were 2 8s in there instead? Then it would be 6. That suggests to me that I should do what? Have another step before that. 2. Determine how big the new array should be. Dot, dot, dot. So how do I do that? By iterating over the elements and counting the number of evens. In fact, if that's a common enough occurrence, maybe I should write a function to do that for me. And I'll pass this array off to another function. You count up the number of evens for me and return that value. Right? We're not going to go that far today, though. Right? So help me out. I've already got code to do that down here. For each element, if it's even, then count plus plus. Or num evens plus plus. That means that I need a variable called num evens. Should I leave it like that? What should I do? Anytime you create a function, the first thing you think about is error handling. Anytime you create a variable, the first thing you think about is initialization. Period. Right? Okay. Num evens. Now I know how much space I need. Is it just simply num evens? Remember, malloc is you tell malloc how many bytes you want. In this case, the number of evens in this example is going to be 5. Do you want just 5 bytes? Nope. You want 5 times the number of bytes that each integer takes, 4. So I write num evens times, how do I determine how many bytes an integer takes? Size of int. There we go. And then finally, you do and you should typecast this because malloc returns a generic void pointer. Okay? Good. Now let's go move forward here, right? So I was able to do step 2, step 3, step 4. Right? So now I can add it, array sub I to the new array. So what do I call it? New array sub I is equal to array sub I. Yeah, go ahead. A question? Or no? Okay. Is that going to work? Let's think about it with this example here. I'm going to go down to the next line here to align these things. 5. 5 does not make it into the new array. 8 does make it into the new array. What is the index of 8 in the original array? 1. What is the index of 8 in the new array? 0. Are those the same? Nope. But my code down here is treating them the same. If I've got two arrays that are not always at the same point, what does that suggest? Create another index variable. Index of new array. That's quite long. We could shorten that up. What do we typically use for indices? I. Well, I is already taken, so J. Right? Don't get creative, right? Now, of course, you should initialize this. Where's J going to start? Where do you start at an array? 0. Right? That way, the new array sub J will take on the value at I. J and I will move forward if you're copying something. Right? Let me go back up to the example here. I initially is going to be here, and J is initially going to be... Again, this is where whiteboarding comes in, and because you can draw this stuff, erase it, and move it along, and simulate this. Right? I could open my iPad, but we don't have enough time. Right? All right. So, do we copy 5? No. I moves on. I is now pointing over here, or referring over here. We copy 8 over. What do we do with I? We go to the next element, but what do we do with J at the same time? We move it over here. 3 is not copied, so I gets moved over to 4. J stays where it is because we haven't copied 4 yet. Now we copy 4. J is incremented, I is incremented, right? We're just moving I and J here, but I is always moving forward, but sometimes J is not. Right? So you've got to keep these two things in your mind and make sure that you are using the correct one when you have multiple arrays here. Right? So J, if we copy something open, I should advance J, J++. Right? All done? Let's ask our compiler. With the wall flag turned on so that it tells us, uh-oh, you've got a getEvens function that returns a pointer. Did you return anything? Nope. So we only know that because of the wall flag. I believe that it won't tell you. Yeah, they'll say that's perfectly fine. Wall flag, wall flag, wall flag. Always, always, always. Right? It's telling me that I should return something here. What should I return? The new array. Okay. All right. That's not going to be too interesting with primes. So let me create another other array with numbers. In fact, let's do it with my my example here. How many elements are in there? 1, 2, 3, 4, 5, 8. Okay, I can reuse n then, right? And int star evens is equal to getEvens of other array and n. There we go. Now let's print it out to see if it actually worked. Print array evens. Is this going to compile? Nope. So if you want to print an array, if you want to pass an array to any function, what do you need? You need the array, and always, what's the second thing that you need? The size of the array. Okay, well, the size of the original array is 8. That's how I was able to get the evens, but when it comes back to me, do I know how big it is? Well, in this particular example, I know how big it should be, 5. But, okay. I don't know how big it's going to be. This gets into a question of who's responsible for what. We've got two functions here. We've got main, and we've got this function that is generating the getEvens array, right? Who's responsible for determining how big the new array is? The answer should be main. Anybody? No? Okay, good. This function. All right. Why? Because it already does it, right? It has to do it in order to create a new array. Okay? So if you're now get evens. Get evens, you're responsible for creating this array. You're responsible for determining how big it is. I need to know how big the result is. Can I return the array? So return the array and its size. Can I return the array and its size? Size of new array. Can I do something like that in C? In no language could I do something like this. A function only ever returns one value. This is math, right? Can you have a function with two values? Right? The unit circle, is that a function? It fails the horizontal or the vertical line test. You can't do that. Wait a second. When we introduced pass by reference, we did so that we could return multiple values, right? I forget what the example was that we did, but I think it was a circle. Here's a radius of a circle. I want to know its circumference and its area. I want to know two things. Give me two return values. We're not able to return two things. Right now you're working on converting RGB values to CMYK values and back and forth. You can't return R, G, and B, three values. You can't return four CMYK values. Instead, what do? You use a pass by reference variable. Let's do the same thing here. Not only am I going to return an array, but I'm also going to return the size of the new array. Int size of new array. All right. Now, is that how I do it? Is that passing by reference? What kind of variable is this? It's just a regular old integer. That ain't passing by reference. What's passing by reference? A pointer. Right? So I'm going to give you an array. I'm going to give you the size of that array, and I'm going to give you this bucket. I want you to give me an array back containing only the evens, but I also want you to fill that bucket over there and tell me how many elements are in that array. 5. Right? Okay. Once we know how many evens there are, what do? Something like that. Is that correct? Size of array is a what kind of variable? Pointer. So the left-hand side is a pointer. The right-hand side is a regular old variable. Those don't match. How do we take a pointer and transform it into a regular old variable so that we can set it? Dereference it, which is the star or the ampersand. Star. Good. That's just that thing you need up in your Post-it note until you drive it in your head. And then leave it up there for a couple weeks more. Right? Nobody found that nice cheat sheet. No? Anybody would go out and search for one? Okay. Anyway. Now, here's another gotcha. Right? I see this all the time. Oh, we don't need a num evens. We could do something like this instead. I will undo that. We could just do this instead, right? We could just increment the pointer variable. But then you pull out your big book of PEMDAS, right? And realize that multiplications are done after additions, divisions are done before subtractions, et cetera, et cetera. I've got two operations here, a dereferencing operation and an increment operation. What are the relative orderings of those things? Does anybody remember? I never told you. I don't remember. Actually, I do remember, but I don't care. I don't want to have to remember that crap. So I'm not going to do something like this because it's actually wrong. Right? What this would end up doing is it would end up incrementing the pointer first. This pointer is pointing to memory location 42. Now it's pointing to memory location 43. Then dereference it. That's not valid, right? Because eventually you're going to get to a memory location that doesn't belong to you, right? To do something like this, you would have to put this into parentheses, and then you can increment it, but that's ugly, right? With an F in front of it. Don't do that. If you're going to play with pointers, play with them once and only once to reduce the number of possible error points, number of possible failure points. Right? A local variable, incrementing that, playing around with that, that's all very much straightforward, very, very easy. You'd have to be trying to get it wrong, right? But pointers, you can get them so wrong so easily. Only do it once, and when you're done, okay? This is correct. So now down here, I need to know how big evens is. So int size of new array. And I need to pass that to the function to tell me what the size of the new array is. And I'll pass that right here. One last question. Size of new array. That's a regular old integer, right? But what does this function expect? A pointer. So yet again, we think of that post-it or that cheat sheet. How do I take a regular old variable and transform it into a pointer so I can pass its memory address? Ampersand. Right. GCC this, run it, and excellent. I get exactly only the elements that I want and the size that I want. Right. So often if you're creating a new array, or if you have a function that creates a new array, you likely have to communicate to the calling function how big that new array is. malloc doesn't need to do that because you're telling it how big it is. Right? malloc, give me an array of a certain size. That's my variable, right? You know how big it is. It doesn't need to return. Also, I created an array of size num evens for you, right? You already have that. So it depends on the design of the function, on what you're trying to do in order to like what needs to be communicated back to the calling function. The last question I'll leave you with is we need to clean up. We need to clean up this new evens array. ... Where do we do it? So, option 1. Here, after we've used it. ... Or, option 2. Option 2. Here, after we've created it, before we return from this function. ... So, who likes option 2? Okay. Think about it. Can I return it if I destroy it? I create something beautiful. And I'm going to give it to you for a present, but before I do, I destroy it. Not much of a present, is it? Right? I've destroyed this new array before I gave it back to you. But once I receive it, once I print it out and I'm done using it, okay, now I'll destroy it. Right? You gave it to me. I made the nice present. I give it to you. It's yours to do with what as you please. Right? Okay, now I'm done using it. I'll destroy your present. Right? Which one? Option 1 or option 2? Option 1? All right, option 2? Okay, now I'm seeing down votes here. Right. All right, we'll talk about that on Wednesday then. Who owns memory? Whose responsibility is it to do stuff?